Now, the next thing I want to talk about is why these reactions are slowing down. Why do all reactions slow down? Why, after between 0 and 50 seconds, why was the reaction happening at 4.2 times 10 to the negative fifth molar per second? And then only, a couple seconds later, 100 to 150 seconds, the reaction's, not even going at half of that speed. Why do reactions slow down? Well, let's talk about it. This has to do with something called collision theory. So chemists believe that reactions occur when molecules collide. It is a theory. No one's ever seen molecules collide, right? But we got some pretty solid evidence that, reactant A and reactant B got to smack into each other in order to react, right? So that's called collision theory. So let's imagine we have a reaction where, A and B, oh man, that blew, smack into each other and they make product C, which is going to be purple. I don't know if that's showing up. That's showing up all right for you. So let's imagine that we start this reaction with all reactants. So we fill this, and they're all gases, let's say. We fill this container, we pump in a whole bunch of reactant A, and we pump in a whole bunch of reactant B. And we start our stopwatch and we say go, right? The reaction is going to be the fastest that it's ever going to be right at the beginning when we say go. And here's why. That is when the concentration, the amount of reactants, is going to be at its greatest. And that's when you have the greatest probability of a collision. Okay, in order for molecules to react, they have to collide. And the greatest likelihood of an A and a B smacking into each other is going to be right at the beginning. And as the reaction progresses, as we use up A's and B's, the likelihood of an A and a B finding each other, two reactant particles finding each other, is going to go down because now there's less of them, right? Kind of just makes sense. So take a look. If at the beginning of the reaction is going to be going off like crazy, right? So it's like, oh man, red and blue, boom, they make a purple. And now these, and then it's going to be boom, and they're going to make a purple. And then it's going to be boom, and they're going to make a purple, right? And then it's like, okay, well, now there's less reds and blues next to each other. So now, okay, those, oh, boom, now they found each other. And now I guess these two could find each other. But now, like the now, it's gonna, like, maybe they got to travel a little further. Like these two, now they got to find each other. So now the reaction's starting to slow down. The amount of reds and blues getting used up because it takes longer for them to collide, to find each other to collide. It's going to slow down. The rate that purples are going to be created is going to slow down. So like it's just the reaction, as we have less and less reactant particles in there, the likelihood of two reactant particles colliding is going to go down. Okay, so if you just kind of stop and think about it with collision theory, it should make perfect sense why the reactions slow down as they progress. Rates of chemical reactions, what happens to them? They are not constant. The rate of reactant consumption and product production always decreases as the reaction goes on. And eventually, if you're super into calculus, eventually those rates are going to plateau. They're going to reach a limit, right? So if I'm tracking the rate of reactant consumption, I got a slide on this in a second, but if I'm tracking the rate that the reactant A goes down, that's going to decrease and then eventually become constant, right? I'm not going to lose any more A. Same with B, okay? I'm going to use it up really fast in the beginning, and then it's going to slow down, and then eventually the amount of B in there is going to become constant. If I was measuring a product, the amount of product, okay, is going to get created very quickly, and then eventually I'm just not going to make any more product, and the amount of product in there is going to plateau. So if you make a graph of, change in reactant concentration over time, you'll get a graph like that. And if you make a graph of the change in a product concentration over time, you get a graph like that. Okay, it's an exponential thing because the rate is constantly slowing down for both of those. Okay, awesome. I love it. I got a slide here, shows exactly that. I did more of the math. So we did the math for 0 to 50 seconds. It was negative 4.2 times 10 to the negative fifth. And then we did the math for 100 to 150. And that was 2.0 times 10 to the negative fifth. So I got all that worked out here. And you can see, right, there's our 4.2 times 10 to the negative fifth. I got the negative up here, so that's why it's not in the table. And then I got the rate at 100 to 150, the 2.0. You can see if we had calculated it from 50 to 100, would have been 2.8. And you can see if we would have calculated from 150 to 200, it'd be even slower. It'd be the 1.4. So, yeah. Now, let's talk about what kind of rates these are. These rates, ladies and gentlemen, are average rates, okay, as opposed to instantaneous rates. What does it mean to be an average rate? Well, an average rate means that on average over that time interval, that's what the rate would be. So I think you guys all, if you stopped and thought about it, are smart enough to figure this out, right? It's not like the reaction is going at 4.2 times 10 to the negative fifth from 0 to 50 seconds. And then as soon as 50 seconds happens, it switches to go to 2.8 times 10 to the negative fifth, right? And then once 100 seconds passes, it slows down to 2.0 times 10 to the negative fifth. That's not what happens, right? Okay, the reaction at the very beginning is going a little faster than 4.2 times 10 to the negative fifth. And at 50 seconds, it's going a little slower than 4.2 times 10 to the negative fifth. But the average rate of the reaction from 0 to 50 seconds would be that 4.2 times 10 to the negative fifth. Same thing for each one of these time intervals, right? Okay, the reaction would be going a little faster than 2.8 times 10 to the negative fifth at 50 seconds. And by 100 seconds, it's going slower than that. But on average over that time interval is 2.8 times 10 to the negative fifth. What if I want to know the specific rate at a specific moment in time, like at 51 seconds? Okay, what if I don't want the average? What if I want to know exactly how fast that reaction is going? Well, if you want to do that kind of stuff, that's called an instantaneous rate. And an instantaneous rate can be found by plotting the reaction graph and then finding the slope of the tangent line at exactly that moment in time, or by using an integrated rate law, okay, which is what we'll get into on Wednesday. Let me show you what we're not going to do this tangent line stuff, but for those of you that have been through some higher level math classes, you know exactly what I'm talking about. If I want to know the speed, so here, let's first acclimate ourselves to this reaction. We got a synthesis reaction going on here. H2 and I2 colliding to make two HIs, okay? On this graph in red, it's the rate of the, no, I'm sorry, in green, it is the rate of the H2 consumption. See, the H2 concentration is going down, concentration on the Y, time on the X. And the red is the rate of the HI production, the amount of HI we're making. And you can see that's going up over time. And you can see that it is constantly changing, right? It's not static. It is, the reaction is slowing down no matter what you look at, right? So what if I want to know the rate of the H2 consumption at exactly 40 seconds? Well, what I would have to do is I would have to, find the slope of a tangent line at exactly 40 seconds, and then I could get the rate, right? And what I could do here is that I could also do that for a product. I could find the slope of a tangent line at that specific point in space. That's a terrible tangent line. But, if I did a straight line right at 40 seconds there, okay, oh, my mouse can't do it. Okay, but you get the point. If I got the slope of a tangent line at that specific point, okay, you could also measure the rate, and that would be an instantaneous rate. Now, the instantaneous rate should also be related by the coefficients, right? So the rate for HI should be twice as fast as H2. And if you do this, you can see that the H2 is negative 2.8 molar per second. That should be molar per second. Oh, no, that's negative 2.8 molar per 40 seconds, okay, or whatever. And then this would be negative there should be positive 5.6 per 40 seconds. You can see it is going to be double, though, for that, right? Because the change in concentration is double because of that coefficient of 2.